Okay, so what you're going to do is you're going to go through and follow along. This lab is fairly straightforward, but I'm just going to show you the parts that you will need to do each section of the experiment. And then we're going to talk a little bit about Bragg diffraction. Okay, so for the first part, you just basically are learning to set up the system. So in the white box, and also too, I will tell you this, most of these boxes have an equipment manual in them if you have other questions. So if you don't have one in the box at your station, go look in one of the other boxes. It'll have one of these in it that'll tell you more about what's going on. So usually what I do is I just lay stuff on the floor. You're going to need this thing with the movable arm. There's a fixed arm and then there's a movable arm on here that you can use. This is the thing that's sometimes called the goniometer. All right, so a goniometer. So you'll need that. And that's pretty much for everything we're going to do. Then you need the transmitter and receiver. The receiver is the one with the scale on it. The way that we're going to measure maxima is through current flow. Okay? We can't see microwaves, obviously. But the way we're going to measure maxima is through this current flow meter up here. So it's got different sensitivities on it. So if it pegs out or it's reading 0, then you might want to change the sensitivity to see if you can pick up a signal. Okay, so the way you do that is with this dial right here. So maxima are going to be read by maxima of current, not because we can't see what's going on. So this is going to read current. Notice that the bell antenna here, if you look in it, it's not square, it's rectangular, and that matters. Okay, so making sure that your transmitter and receiver are both oriented the same way is helpful. Usually I turn them this way. All right. Then the transmitter is the other one of these bell-shaped antennas. Okay, the other one of these bell-shaped antennas is here. Okay, this is your transmitter. It has a power plug on it that you'll need to get out of the box and use. So you will need access to a plug-in. But remember, all these tables are wired, so all the plugs on the ends of the tables should work to plug them into. Okay? All right. Make sure, though, because sometimes the wrong power supplies get put in here. So this is a 9-volt DC power supply. Before you plug in the power supply, make sure it's a 9-volt, not a 12-volt, because we have cooked a couple of these diodes in here by using the wrong power supply. They should be the right one, but just in case somebody's gotten into these and messed with them, it has happened. So just make sure you double check 9 volts DC, 9 volts DC on your power supply. You're gonna plug that in. There'll be a light that come on. It'll tell you. Now, how are you gonna set these up to be able to use them? Well, in your box, you have these stands, okay? Now, these stands are slotted so that they will slide on to these arms, like so, okay? For you to be able to move this back and forth. So this is gonna hold it onto the arm. Then, you've got an opening in here, and you'll notice on the back of both of these, there is a knob you can just undo. Like so, and just undo it like that. And then you'll just put that through the back here. And you'll notice there's a little notch in here that you can use to read the angle. Okay? All right. Okay, so take that back off. But you'll put those on your arms. Now, usually what I do is I put the transmitter on the fixed arm and the receiver on the movable arm, just because the receiver is not plugged in, it's powered by batteries. So if you, or you can, okay, if it doesn't have batteries in it, some of these are battery powered, and so this one's electrical, so make sure you plug that one into. Again, 9 volts DC. So some of the older ones will be battery powered, The newer ones are electrical, but I usually plug in my transmitter on my fixed arm and my receiver on my movable arm, okay? So transmitter without the dial, receiver. If you forget, it tells you on there which one is which, okay? All right. So the first thing that you're going to do is you're going to start out with these two things basically just facing straight toward each other, just to make sure that everything is working, to make sure this is picking up this, okay? So the first part of the section says preparation for system. All you're doing is making sure that these two are talking to each other, okay? All right. All right, polarization, we're going to use equivalent of a polarizing filter for microwave. So in your box, you have a bag of different plates and things, all right? You will need these magnetic stands. Now, these also slide on, all right? These also slide on, so you'll probably have to put these on before you put on your transmitter or receiver. But these have magnetic strips on them to hold the plates. Now, if you've read about polarization, you know that has to do with the orientation of the electric field. So basically, it's a filter. Well, for visual light, we can't see the slots in the filter, but for microwaves, the wavelength is big enough that we can see the slots. So these are polarizing filters for microwave objects, all right? So you can put them on this magnetic plate. You can orient them in lots of different directions to see what's going on. And then there's a question in there to ask to say, which way is this thing polarized? This thing has got magnetic strips on the front and the back, so you can put them together like that if you want to. So there's all kinds of ways to investigate polarization with this by changing the angle. So all you're doing is adding this for the second section for polarization. All right. The next part, interference. You're going to build a double slit. This is probably the trickiest part, and it's just building the slit, okay? So in your box, you have a long magnetic strip like this, and you have it's got a backing on it. This sits on one of these, like so. All right, so it rests on that. Okay, then you're going to build a double slit. Now, remember that the rules for the double slit are the opening size of the slit needs to be on the order of the size of the wavelength of the light. Well, if you read on the transmitter, or if you read in the book that comes with it, it tells you around what the wavelength is. Or if it doesn't, it tells you the frequency on here, and you know the speed of light, and you calculate the wavelength. Okay, it's centimeters. It's on the order of a couple of centimeters. So what you have in your bag are some metal plates. You have two larger ones that are the same size, and then you have two smaller ones. Okay, so to build your double slit, these need to be the outside. The bigger ones need to be the outsides. And then one of the smaller ones needs to be the inside. And then you can adjust the size of your slit accordingly. You need them to be you need the two sides to be the same size. So there are rulers in the back part of the room. You can go grab one, or you can knock it apart. But you can go grab one, and you put your slits on here, and you just adjust your plates until your openings are the same size. And see why it's tricky? Because these things fall off. Okay, so you'll adjust those till they're the same size. All right. Then you're going to put those on your stand. Okay. Now, once you figured out which way this is polarized, you want to make sure that you keep that orientation so that it matches up with the slit opening. So if it's horizontally polarized, you want to turn the thing so it's vertical. That way it'll go through the slit openings. All right. So that's going to be your slit. You're going to put that on one of these, and then you're going to look for the central maximum and then the resulting other first, second, third, fourth maxima by taking the arm on your movable arm with your receiver, okay? A lot of pieces, okay? So your receiver is going to be on this movable arm. So when it's set up like so, your transmitter's here, your receiver is here, you're going to be measuring the central max because you're directly across from the slit open, the center of the slits. Then what you're going to do, upside down. What you're going to do is you're going to sweep this out to look for the different maxima. So that's what would correspond to, if you had a screen up here, that's what would correspond to the different bright fringes that you would see on that screen. So as you move this, you're going to look for, what'll happen is it'll be a maximum in the center because that'll be the central max. Then as you move it, the current will drop because you're going to that first minimum. Then as you keep moving it, it's going to shoot back up. It won't be as strong probably as it was for the central maximum, because remember your central maximum is your most intense, but it'll shoot back up and that'll be your first maxima, and then it'll drop, and then your second maxima, and so on. So you're going to sweep out to try to find the maxima from the double slit to see if you can find it. And you can use that to figure out the wavelength also of your microwave. All right, because remember, the double slit equation depends on wavelength. Where the maxima are at are going to depend on the wavelength of the light. If you haven't read that section yet, when you get to it, it'll explain that. So that's the interference. That's the interference section. Now you can plot this on a polar graph, and it'll show these really pretty lobes about where everything is the maximum. Okay, reflector plate. Well, reflector plates for microwaves look like this. Okay, they don't look like mirrors, they look like this. So this is basically tile board is what it is, same thing the whiteboards are made out of. But these are reflector plates for microwaves. So you're going to verify the law of reflection. Okay, so again, you're going to put this on one of these holders. Now, if you want to center these holders, you can do that. Okay, you've got some of these holders where you can center them more, but you're going to basically use this as a mirror, all right, for the microwaves. Again, if you don't know how to set something up, remember this handout has got directions that shows how to set different things up in it, okay? And this should be in your box. If not, one of these boxes has a complete manual in it, and you can get that and use it. Okay, so if you forget how to set something up, it'll be in there. All right, now, so that's all of our little magic plates we've got here. So let me put those up really quick. Then we're going to make a prism. All right, we're going to make a prism, and you will need 2 things out of your box, or 3 things actually. You need something. The prism is in 2 parts. You need this styrofoam prism, and notice it's got a cavity in it because you're going to fill it with these pellets. Now, here's the tricky part. Don't spill these everywhere. Make yourself, take you some paper and make yourself kind of a funnel to put down in this prism to pour the pellets in there, okay? Don't try to just pour them from the jar, okay? Make yourself a little paper funnel to pour them down in there. When you get ready to put them back in the container, do the same thing. Do not try to pour out of this into that container, or you will be an unhappy person, okay? Because you're going to scatter them everywhere, and then I'm going to be unhappy because I'm going to get a phone call dropping me out because there's pellets all over the floor. So please don't do that. But this is what you're going to pour in here for refraction. This is the refractive medium, okay? Now, you will need a protractor because you need to measure the vertex angle of this prism. This part is going to face the transmitter. The flat part is going to face the transmitter, okay? We want that because that way there is no refraction on this boundary because it's coming in at 0 degrees from the optical axis. So this part needs to be facing the transmitter, okay? Where the refraction is going to occur is going to be here, okay? Because it's just going to go straight through. Then when it hits here, it's going to refract as it goes from this medium to the air, okay? So you need to know some things about this. So you need to measure these angles here so that you can find the angle that this comes out at to the normal. Because remember, refraction is about the angle it makes from the normal. So for this side, the normal to this is going to be like that, right? Okay, so I'll put you a protractor out where you can find one so that you can measure the angles, okay? So you'll need that. All right, so but that is going to sit in the center of your system. If you'll look here, you've got this center turntable with angles marked out on it, okay? And that's where you're going to put your reflector plate also. But for your prism, you've got this fancy little turntable that you can put on here, okay? And you can sit your prism on that, all right? All right. Because this doesn't have any magnetic part to it, so you need this. All right. Again, if you forget how to set something up, you have the manual. You can look it up in there. All right. Now, so that's the next part with refraction. The last part is where we talk about crystallography. All right. When you look at a crystal, crystallography is useful because it is a way to do non-destructive failure analysis, okay? We can look at the structure of something with x-rays, like Rosalind Franklin did, to determine its internal structure. Now, we don't have x-rays here, we have microwaves. So instead of looking at a crystal-sized crystal, we're going to look at an extra special-sized crystal. Here's our crystal. Okay, here's our crystal. All right, these are our atoms. Okay, so we've got layers of these things. So we've got these ball bearings are in layers inside here. Okay, now what crystallography does is it lets us look for flaws in the crystal by finding places where the atoms are missing, or it lets us determine the spacing and orientation of the atoms. So we can shine an X-ray into a crystal and we can look at something called the grazing angle. And that's what all that discussion is about on those next pages. Okay, it talks about the grazing angle. All right, now microwaves, the reflex klystron is the same as the transmitter. That's just a funny name for it, but we're going to use that as our X-ray. So we're going to replace X-rays with microwaves. And what we're going to do is we're going to shoot these X-rays in here. Now, if you look at the next page where it talks about the grazing angle, what happens is the X-rays come in, okay, and some of them hit these guys and bounce off. It's called Bragg diffraction, but it's really reflection. So what happens is the microwaves come in, and when you get it to the right angle, they're going to hit these atoms and they're going to bounce out. So we know that the rule is, in this picture, the angle of incidence equals the angle of reflection. So what's happening is these microwaves are coming in. Some of them are hitting the first layer of atoms. Because of their orientation, some of them are hitting the next layer. And we can use the angle that they bounce out at, or what's called the grazing angle, to find this spacing here. Okay? So Bragg diffraction lets us determine the spacing between the layers. It can also help us determine what the organization is, and that's what the next pages show you. It shows you what the different planes are called. So when you look at just the flat plane that you're on, that's called the 1, 0, 0 plane. Think of that as X, Y, and Z coordinates, not 100. Okay, so X is 1, Y is 0, Z is 0. So these are also in your handout, okay? So this is the 1, 0, 0 plane. You're just looking at a flat plane. Then if you're looking in 2 dimensions, so you're looking at, instead of the spacing, say, this way, you're looking at the spacing diagonally here. You need 2 coordinates. You need an X and a Y coordinate. So this is the 1, 1, 0 plane. So looking at the spacing of these rows this way, like this, that's the 1, 1, 0 plane. Then if I wanted to go through the body and look at how these layers are spaced from here to here to here to here, that's the 1, 1, 1 coordinate, because now I've got X, Y, and Z playing on it. Now we're only going to do 1, 0, 0. Don't try to do anything else. So basically you're going to use Bragg diffraction to figure out this spacing, and then you're going to measure this spacing, and you're going to see how good a job you did. Okay, now, and the reason that's important is that lets us talk about all these different faces. So when we have a crystal, if we want to know its crystalline organization, we use X-rays to determine. That's what Rosalind Franklin was doing when she was looking at DNA. She was looking at the spacing between these things and determine the double helix structure. So you look, different crystals have different properties because their atoms are organized differently. The reason diamond is diamond and not graphite is because the carbon atoms are organized on what's called a diamond lattice. It's not pictured here, but it's organized on a diamond lattice, and that's why it's so hard, is because it has that particular organization, all right? And so when you take something like you take the chemicals and you put them under heat and pressure, like you do with the gemstone formation, they organize into these crystalline structures. When we get to this next unit, we're going to talk about the Davison-Germer experiment where nickel was crystallized because it was heated up and it allowed the atoms to organize into crystal structure. So, but we can use the crystallography to figure these organizations out. Okay, so what you're going to do is you're going to make sure that your little microwave transmitter is working in the first part of the Bragg diffraction. Then you're going to look for the grazing angle, okay? So here it shows you, that, again, the 110, the 10, 110, or 100, 110, and then they do 210. We're not going to worry about that. Okay, so what you're going to do this is you need your turntable again. And you're going to set it on the center of this arm, all right? Then you're going to try to keep the same angle between the transmitter and the receiver. So that's why it says in there you're going to rotate the cube 4 degrees, and then you're going to move one of the arms 2 degrees. So you're splitting the difference between the two arms, all right? Because what you want to do is you want to keep this angle here symmetric, okay? So you're basically going to move the table, then you're going to move the arm to make sure that the angle between the different layers in these two arms stays like the angle of reflection. Now, you may not measure anything at that angle, and that means there's no Bragg diffraction. So then you're going to move it again, and 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 you're going to find the places where you get maxima. So you may move this several times and not get anything, but then all of a sudden you'll get it at the right angle where you get these two light. Basically what you're doing is you're looking for these two things to match up and be in phase, and that'll give you a maxima. So the light that's reflected off this top layer matches up with the light that's reflected off the bottom layer in terms of its phase, and you'll get a maxima. And that'll tell you now I've lined this up right so that I've got this situation going on. Does that make sense? Okay, because if you're not at the correct angle, these two guys won't be in phase, and you won't get a maximum. So there's only certain angles where that'll happen, and it has to do with when you get this nice, this angle correct here for the spacing for your particular crystal. All right. So that's probably the hardest part is finding those angles. I will tell you, I think the first one is around 22. If I remember right, it's around 22. And I think you can get 2 or 3 if I remember right. I know you can get 2. I can't remember if you can get 3 or not. But yeah, so this is going to give us a chance to do some crystallography. Now, you need to measure this spacing in here. So use your ruler, because you're going to calculate the spacing, and you're going to have a measured spacing, and you're going to compare those two, doing percent error. Okay? All right. Again, if you don't remember how to set it up, go back to this. If you're not sure what I'm talking about in my handout, go back to this and find out how to set it up. Okay? So all of this is here. All of this is here for you to use. All right? When you're done, please pack it all back up in the box, okay, so that we have it for the next person to use. And make sure, again, if something is missing, go over here and get it, but make sure if you take something out of the kit, you set it to the side and say, hey, we're missing this part, or hey, this power supply is not working, or hey, the battery is dead, or something. The power supplies in these new kits are in these boxes here. So these are your power supplies for both your transmitter and your receiver. So make sure those get put back in the box. Basically, when you come in, you should have 2 boxes sitting on your table with a protractor and a ruler. And when you leave, you should have 2 packed up boxes sitting on your table with a protractor and a ruler. All right? But please make sure everything is there when you pack back up, okay? Again, if you can't find a user's manual, these boxes over here, there are some complete user's manuals in one of them or 2 of them. So go through and find one, okay, if you need it. All right, so that's pretty much the gist of the lab. So pretty straightforward. You're just verifying all of the phenomenon for reflection and refraction. All that stuff works for all light waves, not just visible light. So when we talk about things like telescopes, for example, the reason, you know, all telescopes are reflecting telescopes if they're research grade. It's just the reflector looks funny if it's for radio waves or for microwaves or for X-rays or whatever. But they're all reflecting telescopes. We use the idea of these mirrors to focus the light. Okay? Does anybody have any questions about the lab before I stop the recording? And if you've got one, I can't see, but just some of y'all, let me just unmute yourself and speak up if you've got a question, because I can't see everybody the way I've got this set up.
So, are you going to post this recording somewhere?
Yeah, it'll be like just like I did before, where I put it under the lab assignment. Like when I did for that speed of sound lab, I put the recording up with the lab assignment in the same tab so that you can find it. So yes.
Yeah, thanks.
Yeah, it'll be there for you to go back and reference as you need to. So remember, what you're doing is you're trying to gather enough information so that if you have to write a lab report on this, you can do it, because we can't guarantee you would have access to this to come back and look. So, you know, taking note of product numbers, taking note of model numbers on things, making note of divisions on the units of the different measuring instruments will be really important for you to do. I would highly recommend photographing your setups for this lab so that you have them, all right? Because if I ask you a question about it on the lab practical, you know, describe the setup for Bragg diffraction, you could look at your picture, or you could insert your picture and label it. Or if you draw this out as your lab report that you have to write up and you need an equipment diagram, you've got your photographs. So what I would highly encourage photographing every step of the way on this lab so that you have, you know, what the setup looks like. Okay? All right, other questions?
For the lab practical, are we going to be, will we actually come to the lab and have to?
No, we won't be able to do it that way. It'll have to be referring back to your lab notebooks. Yeah, it'll probably be one of those things where I can't do it like I normally do, where we got stations set up. So I'll create a document and different parts will, I haven't quite decided how I'm going to do it yet, but I might make it where different parts come up at different time intervals and you only have a certain amount of time to do them. So you would have to be available during that time period to do the lab practical. So like this one might be up for 30 minutes and then this one might be up for 30 minutes and then this one might be up for 30. I don't know. I haven't decided how I'm going to do that yet. But no, you'll do it at home. So it's going to be a little different than what I traditionally do. Since I can't have you show me a setup, I may have you describe a setup. Okay. What else? Anything else about the lab for today? Okay. All right. Well, I don't have anything else for today, so I'm going to end this recording. The Google document is available for you to go and sign.